Now let's look at how we can calculate the moment of inertia about inclined axis. So far what we had, we calculate the moment of inertia about the x and y axis. But what if we have an axis that is rotated about x and y? Before that, let's quickly look at the case why we might need to do this calculation. And for that purpose, let me first draw um, an example. So assume I have a piece of wood um, um, similar to this. So I would have three of them sitting here side by side. So, so the second one is again this exact the same piece. And then the third one, again exact the same piece. So assume we have the same piece of wood is in um, three format and in three of them, and they're sitting on similar, assume the support. And now for the first one, and assume the y I have here is going to be my, for example, this is going to be the x-axis along this edge. It's going to be x. This is the one I have, the vertical is going to be y-axis. So along this edge, and the z is going to be normal to that cross section. So assume these are what we have. Now if I come here and put a force on here, assume I apply force at the center of that, um, parallel to the y-axis, like this. So if you look at that, it's gonna start to bend about this x-axis. So it's the x-axis. So that piece of wood would be bent about that x-axis. So if I draw that cross section from the front view, this is the cross section we have, the cross section of that, and it's start to bend about x-axis. And then this is how to actually look at that, how it's going to be resist about the bending and how much bending it can tolerate. We will calculate the moment of inertia about the x-axis. Now if I come here and have the very same force, so assume this is force F, assume to have the very same force, but this time I applied again about the uh, uh, parallel to the x-axis. So here, assume I'm gonna put that force here parallel to the x-axis, the same force F. This time, if you look at this, it's gonna start to bend this piece of wood, but this time it's gonna bend about this axis here, which is the y-axis. So it's going to start to bend about the y-axis. So if I draw that cross section from the front view, if I look at that, that is going to start to, so if it was the x-axis here, it's going to bend about y axis. And here we can calculate the moment of inertia about the y-axis to see how it's gonna bend, or how it's gonna resist against bending. So here we calculate the I about the x, the moment of inertia about the x. Here we calculate moment of inertia about the y to see how it resists about the bending. Now assume for the third case, I have a force that is not either parallel to the x or y. So assume I have a force here. I apply the force somewhere here, and it's not parallel to either of the x or y axis. So assume I'm gonna apply the force like that. So it's not either parallel to x, y, or z, somewhere there. So when it's gonna bend that, this time when it's gonna bend, it's not gonna be bended, that cross section is not gonna be bended against either of the x-axis or y-axis or z-axis. So basically I'm just assuming it's gonna be get bended about some axis. Assume it's gonna be this one. Not know exactly, but assume well, let me make it a little bit steep. So assume this is the axis, this one is gonna get bended about that. So if I draw it from the front view, the axis that is going to get bended about it is going to be something like that. It's the axis AA. Now we want to see how we can deal with this one, how we can measure the moment of inertia for if that cross section bending about this axis. It's not a, we already learned how to calculate it about the x axis, how to calculate about y axis, but what if it's bending about the axis similar to that, how we can calculate the moment of inertia for that. So here assume that we have x and y axis. The x and y axis, and then we have cross section in this x and y axis, and we do the calculation for that. Now assume for any reason we have new axis which is going to be rotated. So it's going to be the u axis and the v axis, which are rotated about theta in these cases. So we want to know how we can calculate the moment of inertia for that. So in these cases, that for the initially we know the ix, so we know them, so we know the moment of inertia about the x, we know the moment of inertia about the y, and we know the product of inertia about xy. If we know them, therefore we can go ahead and say that we can calculate the moment of inertia about either of these three axes. So for the moment of inertia about the u axis is going to be ix plus iy divided by 2 plus ix minus iy divided by 2 cosine 2 theta minus ixy sine 2 theta. The moment of inertia about the v-axis is going to be, again, is going to be ix plus iy divided by 2 minus ix minus yy divided by 2 cosine 2 theta plus ixy sine 2 theta. And the product of inertia about uv is going to be ix minus iy divided by 2 sine 2 theta plus ixy cosine 2 theta. So if we know the ix, iy and ixy, which is we already know how to calculate them. So the moment of inertia about the x, the moment of inertia about the y, and the product of inertia about xy, then we can simply use this calculation. If we have the axis rotated for theta, then we can use it in this equation to calculate the moment of inertia about those rotated axes that we have. One point about this is that uh, assume that we start here from 0. Assume we consider the theta as 0, and we start to rotate it, and for every value of theta we calculate this moment of inertia. Eventually, if we calculate the moment of inertia for all the theta, we would find two specific values. The one of them is going to be the maximum moment of inertia, and the other one is going to be the minimum moment of inertia. So one more time, if I start the theta from 0 and keep rotating it and calculate the moment of inertia for all the angles, we would find two angles that for those angles the moment of inertia is going to be minimum and maximum. For those specific angle that moment of inertia is going to be maximum and minimum, we call them the principal moment of inertia. So principal moment of inertia. So the principal moment of inertia is basically those IU and IV which we could keep turning until we find the maximum and minimum. And for those axes, when the maximum and minimum moment of inertia happen at those axes, we call them the principal axis. Now how to find those axes, what are those axes, where those axes happen, where we have uh, that maximum. In other words, if I know the ix, iy and ixy, where at what angle those minimum and maximum moment of inertia is gonna happen, which axis is gonna have that, and those axes are the axes that satisfy this equation. So if I have the tangent theta, tangent 2 theta is equal to negative I xy divided by ix minus iy divided by 2. So this is if we solve this equation, eventually this equation is gonna gives us two values, um, mm, which is gonna be one of them. So it's gonna gives us two values. So this equation is gonna gives us theta p1 and theta p2, and these two values are uh, are associated with the I max and I min. So it gives us two values that one of them, at one of them, we have the maximum moment of inertia, and at another one, we have the um, at another one we have the minimum moment of inertia. Um, Remember, the point with this true angle is that the uh, what should not the theta p1 and theta p2 are 90 degrees separated or apart. In other words, wherever we have the maximum or minimum, wherever we have at whatever angle we have the maximum moment of inertia, we have to rotate 90 degrees to get to the minimum one, or the other, also the other, in any other angle we have the minimum moment of inertia. If we rotate for 90 degrees, we get the maximum moment of inertia. So always the maximum and minimum moment of inertia exactly happens 90 degrees from each other. So at whatever angle one of them happens, 90 degrees from that angle the other one would happen. And then we have the magnitude of them. So it tells us where it's going to happen, and the magnitude of them, the max and mean, is going to be ix plus iy divided by 2 plus minus ix minus iy divided by 2 squared plus ixy, and then a square root of that. So also the maximum and the positive is for the maximum, the negative signs for the minimum. So this is also its magnitude. So this equation tells us where we have the maximum and minimum, at what angle we have the maximum and minimum moment of inertia, and this equation tells us what's gonna be the maximum and minimum moment of inertia. Now let's look at what's the Mohr circle for moment of inertia. Uh, Before doing that, so assume again I have my x and y axis here. That's the x and y axis, and I have a cross section mm, in this um, um, system that I have, and for example, this is my cross section, and then I know its moment of inertia about the x and y axis. And now if I assume if I start to rotate x and y axis, eventually I get to then u and v axis, eventually assume I keep rotating until I get to the u and v axis in a way that the moment of inertia about u becomes maximum. So assume this is the theta p. So I start to rotate x-axis until I get to the u where the maximum moment of inertia happened at that axis. If the maximum moment of inertia happened at the u, the minimum moment of inertia would happen at v because it's 90 degrees apart, as we said. The maximum and minimum value of moment of inertia are 90 degrees apart. So if the u is the axis that we have the maximum moment of inertia, the v is going to be the axis that we are going to have the minimum moment of inertia about that. So assume we start rotate and we get to that point. In this case, again, I will write the equation of the maximum and minimum moment of inertia, which is going to be the I max and me is going to be the I x plus iy divided by 2 plus minus square root of ix minus iy divided by 2 squared plus ixy squared square root of that. So one more time, again, assume we start to rotate the x-axis until we get to the axis u, that the maximum moment of inertia happen at that axis at the angle of theta p, and when it happens, let's assume it's theta p1, so where the maximum one happened, and then 90 degrees from the theta p1 is the theta p2. So if I go ahead 90 degrees from the u, if I go 90 degrees, I will get to v axis, which is going to be have the I minimum at that location, so the minimum moment of inertia. Now let's look at the Mohr circle. The Mohr circle is a way that we visualize this discussion that we have here. So for showing the Mohr circle, first of all, we'll assume we have then the horizontal axis, which that horizontal axis shows the I value. Either it's going to be Ix or Iy or Iu or Iv or any I value, I max or I min. And then we have the vertical axis, which shows the product of inertia. Here I would call it Ixy, but it's product of in general, product of inertia about any two axes we have. Now, for the original case here, we know originally we know three values. We know Ix, we know Iy, and we know Ixy. Now if I go ahead and point these two, so I assume, so go ahead and say, assume I would point them and say, do you want the Ix and Y? Assume the Ix is going to be here. So I mark them on the y-axis, so it's the Ix, and then Iy is here. So I mark both of them on the x and y axis. Now I will go and find 2 points in the 2 points that I want to find are point A with the coordinate of Ix and Ixy. Regardless if it's positive or negative, if it's positive is going to be positive, is negative is negative. And the point B, which is going to be the Ix and negative Ixy. So if Ix is positive, the negative Ixy is going to be negative. If Ixy itself is negative, then the negative Ixy is going to be positive. For this case, assume Ixy is positive. So I'm going to define these 2 points. So one of them is going to be, assume here is going to be Ixy. So one of them is going to be here. So it's a point A, and the other one is gonna be here. So it's gonna be point B. So it's gonna be point A, and it's gonna be point B. So it's the IX and IXY, and this one's gonna be IY and negative IXY. Now if I draw the line between these two from the A to B, and then point out that the the point that is gonna cross the I section, um, cross the I axis as a center, and I will go ahead and call it the O. Now if I draw a circle with the center of that O and the diameter of AB, so I draw the circle with center of O and draw a diameter of AB. So it's gonna be something similar to this. So this is a circle I have. So it has a diameter of AB and goes through the circle. Now if you look at here, wherever this circle happens, this circle basically gives us different condition that we have for the I and IXY. So any point on that circle tells us what's happening if we rotate this axis. So basically here the point A is IX and IXY for the original X and Y axis. Now if I start to rotate here, this is what's gonna hit. This angle, if I start to rotate for 2p 2 theta p1, if I rotate from point A for 2 theta p1, eventually I will comes to this point, which is the I max. It's where we have the maximum value. So if I start to rotate on that circle until I hit that, okay, this is the maximum value I have on that circle. So it's going to be I max. So if you look at here, on the regular axis I rotate for theta p, and here I rotate for 2 theta p. So basically from x to u is going to be theta p. So here on the circle, if I rotate 2 times of whatever I have to rotate here, I will get to the point that I have the I max. Now here from the u, I know that if I go 90 degrees back, if I go 90 degrees back, I would get the IV, which is going to be the minimum value for the I. So for this case, we'll assume that if I rotate for theta p1, I get to the u, which has the maximum. This is what we have here. Now, the I sub v is going to be 90 degrees apart from the IU, and it has the minimum value. So here I rotate 90 degrees. So on the circle, I'm going to rotate 2 times of that, which is going to be 180 degrees, which doesn't matter which way I go. And if I rotate from here for 180 degrees, which is going to be 2 times of 90 degrees that we have here, I rotate, I will get to this point, which is going to be the I, the minimum value for the I. Now, if I look at here, and in this triangle that I have here, if I draw the so let me just make a couple of points. So here to the center, what's the location of the center I have? The location to the center, is Ix plus Iy divided by 2. If I add these two divided by 2, is going to be, so the location to the center is Ix plus Iy divided by 2. If you compare this with this equation, you will see that you have ix plus iy divided by 2, and this is exactly the location of the center. So this part is the location of the center on the y-axis. So this equation, this part, the first part of equation tells us where is the center of this circle located, ix plus iy. And now if I go ahead and let's look at this distance here. So this distance between the center, so the distance between center and the location of that ix, this this distance here. So this distance here is going to be ix minus iy, which is ix minus yy is going to be this distance from the iy to ix divided by 2. So it's a half of it. So this is going to be ix minus iy, which is going to be this distance, and then half of it, which is going to be that distance here. Now look at the, if I draw a triangle here, this triangle, the AOIX, the AOIX, if I draw that, that's a point A, and that's a point O, and that's a point IX. And I know this distance here, I know this distance is IXY, because this is the point A. The point A, we know that is going to be IX and IXY. We draw them, and the B is IY and minus IXY, because we draw them that way. So this distance here is IX. This distance here, the O to IX, this distance, this is what we find it here, we calculate it here, is going to be IX minus IY divided by 2. And then this is going to be the R. So OA, basically when we look at the OA is the R. So that is the R value. And if in this triangle we find the R is going to be this value squared. So IX minus IY divided by 2 squared plus, and this is IXY, not IX, so this is IXY plus IXY squared, a square root of that. Now if you compare this part with this part of the equation, this is going to be the R. So this is the R. If you look at that, this is the R. So, and this is the location of the center. So basically this is where we have the location of the center. It tells me where is the O value, where the O is located, this part. And then this is the R. If we add the R to location of the center of the circle, it gives us the I max. If we subtract the radius from that location of the R, it's going to gives us the minimum value of the IY. So the minimum value of the I, so it's going to be the I min. So basically this equation here, the first part shows the center. This is the location of the center of that. So this is the location of circle center, and this is the radius. So We find the location of the center, we add the radius to that, it gives us the I max, we subtract that, it gives the I min. So you can do this calculation for finding the maximum and minimum, or where they are going to be located, or theta p, all those values we can do it visually by using the Mohr diagram from these calculations. Similarly, also if we uh, look at the uh, remember that we will say that the tangent to p, tangent to theta, uh, we have the tangent to theta p is equal to negative ixy divided by ix minus iy divided by 2. So here also, if you look at those that angle here and that we can assume it's rotating um, counterclockwise. Then in this triangle, so again look at this triangle here. Um, so this triangle, this is 2 theta p. So if you look at that triangle, the tangent of 2 theta p is going to be the ixy divided by this value. So you can also get it from that triangle again. So, and because we can consider counterclockwise, so it's going to be negative. So also you can get this value from this rectangle. So if you draw that Mohr circle, you can calculate all these values, the location of or the angle of the maximum and the minimum axis. You can calculate the theta p, and you can calculate the value of the I max and I min. Now, one more time, how we draw that. Just the horizontal axis is I, the vertical axis is ixy. Then locate the A and B, A and B, connect the A and B, and then when you connect the A and B, make a circle that has the center of O and goes through the A and B, and that is gives you the Mohr circle. Another application for Mohr circle is that we can find the moment of inertia in case that we rotate an axis. So look at here, what we have is that the x-axis and y-axis, and it says that the point A associated with the moment of inertia about x-axis and the product of inertia. Now if I rotate, for example, this axis counterclockwise or clockwise, we can use the Mohr circle to find the moment of inertia on that axis. So for example, if I rotate counterclockwise for theta, then I have to rotate 2 theta on this Mohr circle. So remember, whatever we rotate here, we have to rotate 2 times of that on the circle. So if I rotate for theta here, I have to rotate for 2 theta on axis. So point A is associated with the x-axis, and I rotate x-axis, for example, for theta counterclockwise. So I go to the point A, and I start to rotate counterclockwise, but 2 times of theta. And I will end up at one point on the circle. That point on the circle associated with ix and ixy, those I and ixy are associated with the rotated axis. So for example, if I rotated for 15 degrees here, clockwise, counterclockwise, then I have to come to point A. So I want to rotate 15 degrees. So on the circle, I have to rotate 2 times of that. So it's going to be 30 degrees. So I rotate from point A 30 degrees counterclockwise. And then I ended up one point on the circle. So whatever values that point has, that point has the I and ixy. Those I value for that point and ixy for that point are the I and ixy associated to the rotated axis. Similarly, if I rotated counterclockwise, so assume I rotated at 30 degrees counterclockwise, so it comes to point A, which is the x-axis, associated with x-axis. So I want to rotate counterclockwise, so I rotate clockwise. This time I want to rotate for 30 degrees, so I have to rotate 2 times of that on circle. So for 30 degrees in axis here, I have to rotate for 60 degrees, 2 times of that. So I rotate 60 degrees clockwise, and I ended up at one point, and whatever I and IXY I have on that point, those I and IXY are associated with that rotated axis. So this is how we can use the Mohr diagram to calculate the I and IXY for rotated axis.